I'll just introduce myself, unless you want to. Okay.
It's yours.
Okay.
Technically until 12:30, but we are starting late, so just do an hour and make sure people have time to go back and forth. Afternoon is project time, so it's not so bad.
Okay.
Just don't do another 30 minutes.
Right. So
So you can go until 12:40.
Oh, that long. Okay. Well, we'll see how it goes, but I'm not going to be in any desperate.
Cool.
I'm the only thing between myself and lunch. So. Okay, so this presentation may end up getting interrupted momentarily here and there as things get fixed, but I think it's going to be okay, so we'll find out. I started putting in some adjustments to data directories and so forth. So the idea here is I thought I would just talk for a second about some data visualization as a prelude, because we keep seeing that coming up. And this happens to be an example from some older work that I was doing with some geochemists. And if you are accustomed to the ideas of mass spectrometry, this is a type of mass spectrometry called FTICR mass spec. And the whole point of it is it uses really gigantic magnets to get really narrow peaks. And those can be then kind of sorted into molecular formulas. So each one of these dots here is a molecular formula. And where I'm going with this talk, I should explain, is really to go from some elements of my experience to what we're worried about or what we're concerned with here today, which is kind of ramping up skills. And I particularly am a good kind of proxy for somebody who's clueless, because I am entirely clueless. And so what I wanted to do when I started thinking about this event was be that proxy for clueless and talk about how I've struggled through getting Python to talk to netCDF files and understanding Jupyter notebooks and so forth. But I have a couple of preliminary things that are what I'd say is more meta science. So looking at the discipline of oceanography and science in general from a higher level and saying, what are we trying to do here? So one of the things that we're trying to do is be able to visualize things, and this happens to be a collection of molecules. And you can see that there are different colors. They're color-coded by whether or not they have phosphorus or nitrogen or both. And so one of these dots in here might be like C14H32O5, et cetera. And they're placed on this diagram based on the ratio of carbon to oxygen and carbon to hydrogen. But then there's a vertical axis, which is what is the mass of the molecule. And right down here up in the corner, there's about 1, 2, 3, 4, 5, 6 green ones in a row, and those are separated by 1 proton. So those are all different isomer, each dot can be multiple isomers, but they're separated by mass. And then you'll notice that I have a slider down here, and as I slide, the entire assembly changes its configuration, and it becomes this sort of central peak. So the 2 points are that you can't really see that peak if you just freeze it, but if you move it back and forth, your eyes and your mind is capable of resolving that as a big blobby white peak there in the center. And then if you slide back to here, then you slide back to a mass representation. So one is the peak in the mass spec, the peak height, and the other one is a mass representation. Okay, so this is data that has at least 5 or 6 dimensions, and it's hard to do that kind of thing. It's hard to separate that out and think about it. This is not intended as a solution for that, because there's a lot of idiosyncrasies involved, and there's a lot of, repetitive kind of banging your head against the wall. But this is why I was kind of asking Jake about Altair and what it's capable of. I still think we have a long ways to go in terms of data visualization, and it's an interesting, fun problem to work on. In addition to that little bundle of molecules, this happens to be the Earth. Here's another example of visualization I've worked on, and this is something called CFlow. That's a flow cytometer that's operated here at UW and elsewhere. And Sophie Clayton is a postdoc who's working on it. And so she has a track from Tokyo to San Francisco, and the data is just plotted along that track. And what I like about this is that the center one is chlorophyll, and then one is temperature and one's salinity. But you can see where there's busy activity, and if you can somehow contrive to superimpose some kind of a sea surface temperature map on top of that, then maybe you can start connecting what you're measuring in situ as you're transiting along in a cruise. You can connect that with what satellites see, which is sort of what the Southern Ocean Group is working on is for their project, where we're trying to bring together the moorings and Argo and remote sensing. Okay, so enough of that, on to the talk proper. The idea is that, this thing goes away. Let's see. The idea is that we have a terminal with on our Jupyter hub. If I say PWD, it says that I'm in Oceanhackweek 2018_tutorials/day3/synoptics. So if you go there and you say ls, there should be a glodap, glodap.ipynb notebook. And hopefully if everything is working beautifully, you can go to your Jupyter Hub master directory, find the glodap file there in that OHW 2018_tutorials/day3/synoptics, and start that up. And when you do, it'll look like this, where the first line is synoptic validation. So to explain what I mean by that, synoptic is, I don't know if I'm using it right, but I sort of think of it as multiple sources coming together in one place for consideration. And as we were kind of articulating oceanographic problems, somebody mentioned the idea of bringing data sets together. This is a recurring theme. And in fact, if you were to super generalize that, you could say every bit of oceanographic data that's ever been collected out there has either been thrown away or put under a desk or put on the cloud or put into a DAC, an archive center, or sitting on an FTP server. They're all over the place. And this can sort of drive you to tears if you think about the potential science of that data. And the question often comes up, and I've been having this conversation for well over a decade now, of how do you get those data sets out from shoeboxes and tape drives and make them available. So I work here at UW in data science. I work with everybody from genomics to medicine to oceanography, and thematically we do spend a lot of time talking about using the public cloud as a compute resource, and the reason for the rationale for that is that the public cloud is a place where you can go and do almost everything you want to do with a computer without actually ever buying a computer. So if you're a really rabid enthusiast for the cloud, then you think it's the greatest thing since the personal computer, right? You think it's that kind of a big level revolution. But the problem is that the cloud is a new invention in terms of how do you use it in science. So it's incumbent upon the early adopters to leave a trail of breadcrumbs to make it easier, to lower the barrier of entry. And that's also true for Jupyter Hub, and it's also true for Jupyter Notebooks and for GitHub, for all the stuff that we're learning here. And so one of the things that thematically I think is really interesting is the question of how much time do I have and how do I spend that? Do I want to spend time, for example, learning a whole new programming language? Or if I solve a problem, do I want to spend that much time again creating documentation so that somebody else can come along? And since I'm sort of later in my career, I've gotten really tired of the frustration that I have when I figure something out and then come back to it 2 months later and can't do it again. So I spend a lot of time trying to teach my earlier in time self how to do stuff. And that's what has produced this Jupyter Notebook, Synoptic Validation, which I'd like to go through. And it's what kind of informs my approach to trying to foster cloud adoption in cases where computing resources are really helpful and useful and necessary. And a lot of this comes out of the fourth paradigm, the book that was written kind of inspired by Gray, where we say that we're now in a fourth phase of science where we have so much data that we don't really have any alternative but to make these massive computing machines that are capable of interpreting that data. Otherwise, you end up just in a deluge. And I was first introduced to this when I started working at JPL in the early 90s. because these satellites would go up and they'd be pouring terabytes down every day, terabytes of satellite imagery from radars, and that stuff would all just go into a filing cabinet as hard copy printouts and magnetic tapes, but it would never get used. So there we go. So teaching ourselves is important to me. Recipe coding versus prison coding. Is everybody kind of seeing this? Is there any issues with getting to the notebook? I don't see any signs of that, so I'll assume we're okay and I'll just continue. Oh yeah, one of the things I'd intended to do was to increase the zoom level. Let's see how that goes. Okay, let's see if that works. Okay, so my first cell here, if I run it, it will probably not run. But if I change this to say dot, oops. Okay, so how about this? Control Enter. So the first cell here says import MATLAB, et cetera. And then there's a, it's just a photo challenge. Oh, good, so that works. It worked for me anyway. So before I get going any further, my photo challenge is, does anybody happen to recognize this very happy person? Naomi Oreskes, that's exactly right. So, and I'm mentioning her because, as I said, I'd like to talk about science sort of viewed from above. And she wrote a famous paper where she talked about scientific adoption of climate change, and I've been citing that for years. And then she subsequently gave a TED Talk where she kind of addressed this fundamental issue that I've had with confidence in science. And it's basically, the question is, if it's a logical fallacy to try and assert something by saying, well, the authority over there says that it's true, so citation by authority is a logical fallacy, then since we can't all understand all of the science that we're doing, how can we say that we support all these different fields and their conclusions, including climate science? Because isn't that just reverting to citing authority? And this might be a trivial thing for you to resolve, but I was kind of bothered by it for a while, and I was watching her TED Talk, and she points out that we do in fact work from a type of authority, but it's not the authority of the individual, it's the authority of a skeptical community. And so I thought that was a really nice way of resolving that little problem, and I thought I would point out that people like this who are thinking about the nature of science and making that public argument, it's kind of an inspirational thing to look for and to cite, so I thought I'd mention that, and we'll get back to her a little bit further in a minute. So onward to what's actually going to happen in this notebook. GLODAP stands for Global Ocean Data Analysis Program, and the idea is to go out and take a snapshot of the world's oceans and make that available as a data set. And there's a lot of different parameters that are in that data set. So biological parameters, nitrates, and dissolved oxygen, and in addition to conductivity and temperature. So it covers the entire ocean, and it is from the surface down to 5,000 meters. And so that's a really cool data set, but you might imagine it's in NetCDF format. And I don't really, or when I started this, don't really get NetCDF. So I wanted to try and sort of visibly wrestle with the whole NetCDF thing and model going through banging my head on that to where it actually becomes something that I have some control over and I can use it. There's a ton of data out there. I have a couple of digressions here. So there's tons and tons of data out there. And in addition to the GLODAP data set, the question is, what else is there? So my premise is this synoptic validation to say, if you have an ocean observing initiative station that's measuring something and an Argo drifter happens to go by within 100 miles, are those data which are ostensibly measuring the same kinds of things comparable to one another? What are the sort of error bars? What's the variability across the ocean? And let's go from GLODAP to Argo to the Ocean Observing Initiative to sea surface temperature to other things that are measured by satellites to cruises to gliders to et cetera. The list goes on. Everything that's potentially out there, that whole collection of shoeboxes. Right. So let's see. I want to make sure there's other notes in here about the structure of the data directories and so forth. But if you'd like to think about what I'm showing here today as sort of an encapsulation of a larger project, that larger project is to provide a set of about 10 Jupyter notebooks that anybody could open up and sort of follow along step by step, and it acts as a reference. So you're like, oh yeah, I know, somewhere in there it plots the GloDAP data with a slider that allows me to go up and down. That's in here, and you just can go and copy that code out and use it for the thing that you're interested in. It drove me crazy until recently that I was hitting Shift-Enter on Jupyter notebooks. I would hit Shift-Enter, and it would go, here you go, and then it would boom, scroll down to the next thing. And when it scrolled down to the next thing, I had to scroll back up. And if you do that 73 times in a row, pretty soon you start to really resent the fact that you're always scrolling up. Turns out you can hit Control-Enter, not Shift-Enter, and the focus stays right there. So if you need to do something 73 times in a row, do Control-Enter. Okay, that's probably the most important thing I can tell you today. And there are 86,400 seconds in a day and 31 million in a year. This notebook features the use of Linux. So even though it's running Python, it does some Linux stuff. It imports static images that we already saw with the picture of Professor Oreskes. It plays YouTube videos, and it plays an MP4 animation. And there's another one associated with this called Boto CP, which copies from the cloud to here. So there's a bunch of things that are going on, but probably the most interesting one is the dynamic widgets and the maps. So we'll get to those down below if everything works according to plan. Okay, so here we are. It says run this cell. And let's see what happens if I run it with Control-Enter. Okay, it ran. Okay, so that's good. Next cell says, optional, get YouTube video. And it's set something called get YouTube video equals false, and then it fails to do it, so I'm not going to even run that cell. And I did that because I often just run a bunch of cells in a row, and I don't want it to keep loading the YouTube video, so I put this little bumper in the way. But the third one is called Professor Oreskes Discusses Science and Confidence. It's a TED Talk, so I'll go Control-Enter. There's a pause, and lo and behold, fantastic, this is working. So there she is, and she's going to give this talk. I highly recommend actually listening to the whole talk. At least I certainly enjoyed hearing what she had to say. It was great. Here's another one. This one is going to import Python and then sort of display some audio. So if I say Control-Enter, oh, didn't work. Okay, so Amanda, do you have a perspective on that? Should I just say /? See what happens if I do this. That's more likely. Okay, good. So it's a good day today. Anybody hear that? Okay, you're no doubt thinking to yourself, oh, that's an ADCP. Okay, so that's hydrophone data. That's provided, that's available at the link that's cited here. So it's obviously part of the oceanobservatories.org website. And it's hydrophone data that includes some humpback calls. And we're kind of spinning off some work on isolating what stretches of the many years of hydrophone data actually have interesting biological signals like that. But I wanted to mostly just demonstrate that you can embed audio in a Jupyter notebook. And I also use something called JS Animate to create a bunch of frames of mean sea level anomaly. We'll see if that works. It's not going to work. I think I need to modify this one also. So I'm going to change that directory and go Control. Yay. Okay, so this has loaded up a movie. I can hit play. And this is along the Oregon, California coast. It's just some MSLA data that I got from OSU. And this is, I should mention, this kind of traces its roots into the Distributed Active Archive Centers system, the DACS. If you go to the NASA Common Metadata Repository and the NASA Gibbs websites. Those are 2 NASA resources that are supposed to be like a nexus of data resources. And you can go from there to the various data sources like this one and pull them in and so forth. Okay. So now I'm going to move down to deconstruction. And it doesn't like that. So it doesn't. The data files, no access. Okay. And I think that they were where they were supposed to end up is in something called home/Jovian/data. No, all this stuff should be just referring to the few days ago. Yeah. When directory is backwards in the code. Okay, I'm just going to pause here and say, what should we do? Okay, so there's a data directory up on cell, well, a higher up cell that says run this cell, where it says /home/Jovian/data/glowdap. Home Jovian, and then where from there? Okay, but if I say, okay, and I'm going to modify this notebook so that it runs on my local configuration. Okay. So does everybody want to continue charging on here? Or basically, if you need a couple seconds to get this thing straightened out, just raise your hand and I'll pause. Okay. Not seeing any hands. Not seeing any hands, I'll continue onwards. I see. Okay. Yes. So I didn't actually do this on the first day. No, I did not.
So you want a wget.
Ah, da, 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 da. That. Okay, so Amanda's put the wget command on the Slack on the general channel. So I will proceed slowly while anybody who needs to wget that thing can continue. So, all right, shall I continue then? Right, so your home directory looks like /home/Jovian. So can you look at that? Is that? There should be no quotes. Okay. Okay. So now in my home directory /home/Jovian, there's a directory called data. If I say cd data, there is a bunch of subdirectories that have various data sets, including the audio that we heard, the video, some Argo data, and the GloDAP data. So I'll just charge ahead. I'm now at the deconstructions, the cell below the word deconstruction. And I have 3 GloDAP files in that directory structure. One of them is salinity, one's temperature, and one's dissolved oxygen. And what I'm doing here is I'm just simply saying dataset ds SAL for salinity equals XR, which is an X-array object. And then it says dot open mf dataset, and then it passes the file name. And those 3 lines run without any comment, but then when I type DSO2 all by itself, it prints the structure of the oxygen data set. So that is this enormous printout of stuff here, which I find kind of intimidating. But you'll notice that on the very left-hand side, there's kind of 5 different categories. There's dimensions, coordinates, dimensions without coordinates, data variables, and attributes. And I started actually looking at this thing and staring at it for a while, and I noticed something strange, which is that the longitude here starts at the value 20.5, and it increases 21.5, 22.5. Okay, so it's going in degrees, but it seems rather strange that it's starting at that value, and I have no idea why. Also, it says down here, the description is a 1-by-1 global mapped field of dissolved molecular ox, ... And I'd like to know what actually that says. So I banged my head against it, and I found that I could start printing things like DSO2 and DSO2.oxygen and .comment and .description and .citation and so forth. So if I run this cell, it says at the top, okay, this is an X-array data set, and it does what it did before, but then it prints out something about the oxygen data, and it prints out a bunch of nonsense, which is probably like Norwegian, because the original authors were Norwegians, in some incomprehensible scripts. I'm not going to worry about that. But then it prints a 1-by-1 global map field of dissolved molecular oxygen from the GLODAP v2 data product, et cetera. So this is a success. It's now telling us more about what the data is. There's a huge citation here. And then the last thing that I printed in that cell was DSO2.oxygen.units. And that's how I find out the units of my dissolved oxygen. And here they are, micromoles per kilogram. So fantastic. What about that longitude thing that I mentioned? So let's run this cell. And it says, yep, sure enough, it starts at 20.5 and increases. And so now I have to make sure that every time I refer to longitude in this data set, I'm ready for the longitude to go above 360 by 20.5 degrees. There's also something called inspect in Python, so I can inspect an object. If I do this and run that, I'm trying to inspect DSO2, and I'm getting the documentation. So look, the DSO2 data set, which I'm inspecting, is telling me something about itself. Okay, so again, I'm just kind of trying to work my way through the different features. How about getting to actual numerical values? If I write down the name of the DSO2 data set and put in square brackets oxygen, and then put in square brackets after that, 0 to 2, and 90 to 92, and 120 to 122, those are indices for depth, and then latitude and longitude. So if I run this thing, then lo and behold, it'll actually start printing out a few values. So here's some dissolved oxygen values that I'm pulling out of this magical X-array data set. Similarly, I can run this next one and get a couple more values. So there's some data set from some temperatures. So it's from very cold water and some hot water. And that's just by randomly picking different indices. Okay, so the whole point of this section here has been, first of all, we created these data sets, dstemp and dssal and DSO2, and pointed them at the data resource, the netcdf file. And from there, I was able to sort of, by trial and error, figure out ways of looking into that netcdf file at the guts of it and figuring out how to actually access numerical values. And for me, this is a big thing because I've come from a background of just binary files where everything is just number forever, and you keep the metadata in your head. So now I'm having to get used to the fact that these files are trying to be super clever and have their own metadata bundled along, and okay, fine, I'm finally willing to invest the time. This is why I put recipes versus prison at the top of this notebook. Recipe coding is where you look on Stack Overflow and you find the recipe for the thing you want to do, and then you get stuck 5 minutes later and you go find another recipe and another recipe. And so you just keep on going by little steps like this. Or this notebook is a gigantic recipe. There's also the idea of going and carving out the time to spend a month learning X-array and Dask, like Joe was just teaching here, sort of from first principles. And the problem is that it feels to me like I'm in prison because I have to sit there for week after week and learn this very abstract stuff that I eventually will become second nature and I can come back and apply it. So it's just a problem. Where do you put your time? Where do you bet your time chips? And I think that for me anyway, it becomes a point where if I get frustrated enough, then I'll make the time to try and learn it the right way. But I tend to be really sloppy and lazy and try and do it the recipe way. So, okay, great. Let's move on to interactive sliders. The next cell is called optional. This creates a 2D color-coded view of oxygen at the surface, attaching a slider to a depth parameter. So if this runs for you, it should look like a slider on top of a coarse map of the world. This is the GLODAP dissolved oxygen. And the slider up at the top is an index. It goes from 0 to 32 because there's 33 different depths. And so I recover that depth index from the slider and then use it to look up what the actual depth is. So if I slide this over to 6, I need to make this a little bit smaller because I can't see everything at once. Okay, so if I make the depth index be 6, then it says down at the bottom of the map, this is for water at 100 meters depth. And if I make the slider go further, it goes deeper down. It goes down to 900 meters. So it's just the depth axis. And as you make that slider get bigger and bigger, well, most of the oceans turn very low anoxic, and some of the ocean starts to disappear because it doesn't go down that low. So if I go down to 3,500 meters, the oceans are much smaller. And it's really kind of fun to stare at this and see what ideas it suggests, because just having this kind of access to the data where I'm no longer thinking about the slider, it's just second nature, allows me to start saying, well, how do I understand the fact that all along the Southern Ocean there's that band of red at a depth of 300 meters? So there's a lot of dissolved oxygen at 300 meters in the Southern Ocean. And it also seems to cling to the Antarctic coastline. So that's kind of fun to think about. Let's go down to the next one, which does exactly the same thing, but this is salinity. And if I'm talking a lot, if anybody wants to volunteer observations or other interruptions, ask questions, that please do. The reason I like the salinity picture is because blue is fresh water, so to speak, and salinity of 33. And you can see the Amazon. So the Amazon is making this nice freshwater lens on top of the Atlantic Ocean, and you can maybe see the, what's the big river that comes out of Africa? The Congo, thank you. I got the C, but I didn't have the rest of it. And if I take the slider and slide it down, right, because is that fresh water go all the way down? If I take the slider and put it on 5, the Amazon disappears. So that freshwater lens is gone at 75 meters. What if I go back up a little bit? If I go back up to 20 meters, it's still there somewhat. And then the last one, the next cell below this, if I run it, gives me a picture of temperature of ocean water. And this one, I made the note to myself to go down to 28. So I was playing around with this, and I slid this down to 28 at some point. And I thought, oh, this is really cool, because white is sort of middle temperature and blue is cold. So that whole stripe of white up through the center of the Atlantic Ocean must be like, that's where the center of the ridge is, so that's where the water is really hot. But then it occurred to me, no, that's just where the surface doesn't go down far enough, so that's no data, that's not white. But I also liked this sort of, in the southeast Caribbean, there's this big red patch, which means that down deep, whereas in most of the world's oceans it's cold, down deep in the Caribbean, at that point, it's really warm water. So why? Why is that the case? What causes that water to stick around there and stay warm and sort of inherit the surface temperature? Okay, so that hopefully was of interest, and now you have a mechanism for installing sliders. The philosophy of putting a slider in is you just sort of write the code to draw the picture that you want, and then you realize, oh, I have to keep changing the parameter, like the depth parameter, if I want to look at a different depth. So instead of doing that, I'm just going to indent everything, make it part of a function, and then connect it to this interact widget. And that's the Python trick for creating a control. Okay, so I haven't yet gotten to the validation idea of connecting this to OOI, but I do have a little bit of that to do. And I don't want to keep on dragging this on. I'm supposed to finish at 12:30, so I'll just sort of roll on down. If you see something that you want me to remark on, please do. Let's see if that works. Okay, good. Okay, so I'm now at the cell that's below using nearest to interrogate at a particular location. And I just ran it, and it ran successfully, so that's another reason why this is an excellent day. So what does it mean to query by nearest? So this GLODAP data, as we saw, is at 1 degree increments across the surface of the Earth. And if I have an Ocean Observing Initiative site, let's say the Oregon slope-based site, and that's at a very specific latitude and longitude, how do I compare that? Well, I could go in and try and figure out the indexing by hand with some scratch paper, but there's this really nice feature of the X-array data sets, which is the nearest method. So if you have this up, then you can look at the GLODAP OSBDO list line that I've highlighted on the screen. So GLODAP, that just means this is a data set that I'm going to pull out. And it equals DSO2, so that's dissolved oxygen, dot oxygen, that's the oxygen data, and then dot SEL means select. And then I give it these parameters, latitude and longitude, and I cheated the longitude because the range is bad. I added 360 because of that idiosyncratic longitude for the data set. And then I said method equals nearest. So that what this, and then dot values means the actual numerical values. So what this is interpreted as is go to the GLODAP dissolved oxygen data set. Fantastic. Go to the oxygen. Within the oxygen, go find the place at 44.6 and 125.4, that coordinate, because that's where the Oregon slope-based site is in the cabled array. Okay? Great. Now, since the indices are not going to match 44.6, also use the nearest index that's closest as possible to that location. So now you're able to search into one data set based on the coordinates of another data set without having to, just letting the X-array do the work. And then similarly, it does that with the temperature and the salinity. Okay, so that cell has run, and it also actually, the last line of that cell is plt.plot, so it gives us a quick look. And as you can see, this is still the, what it's plotting is still the GLODAP data. It reaches an oxygen minimum around 800 meters and then goes back up again. So that's an interesting thing that would be fun to look for. It's pending in this work. Okay, so now I'm going to run the next cell, which is a big plot cell, again with the sort of recipe philosophy. And what happened is it gave me a temperature transect, and this is going from negative 60 to positive 60, somewhere in the east central, slightly east central part of the Pacific Ocean. So that's the ocean temperature, surface temperature, according to GLODAP. And as I roll along, again, the depth will drop and it will go and recalculate. So if I go down to the deepest part of the ocean, there's no data. But if I go up a little bit, it's very cold at the bottom of the ocean. And then after I did this, and I went to all this trouble of putting this slider, I'm like, well, this is monotonic. It would be really simple to just look at it all at once. So let's do that too. That's the next cell down. Just takes a moment to run. For a couple moments to run. Or a lot of moments to run. Okay, so I'll just keep talking. Everything that's happened so far has been GLODAP data, and the next section here, we're going to take advantage of some Oregon slope-based OOI data that I pulled into that data directory. Okay, sorry, so here's the vertical profile. So each line is successively deeper, and the very coldest stuff is down at the bottom. And again, this is a 120-degree latitude transect through the Pacific Ocean. So there's a lot of structure there. I just think this is really interesting. Okay, so now we're back to this idea of going to the OOI data. I'm going to just simply run some cells. I've opened up a new data set that's Oregon slope-based, and it happens to be from January 2017. It covers about 29 days, and it's CTD data from a shallow profiler. Okay, this is a little bit of a sanity check just to make sure I can see some dates. There sure enough, is the first day. Oh, I see. This is an older data set. Okay. This may not work because of the data set update that I did, but we'll just continue on and crash and burn. Interesting. Speed pressure is not defined. Okay. Well, the cell above didn't run. The cell below that ran sort of, and so this is sort of, this will be the last thing to show before going on to the Argo stuff, which is that this, there's a double widget here that allows you to choose one of the parameters as well as the location in the cable array. Okay, so I'm going to move on to the Argo stuff just to finish this up. So I also did an Argo search and pulled in some data from that. There are 9 different Argo floats in the time of interest that are in the area. I'll print. Again, just printing the Argo, the first of the Argo data sets, actually it's the second one because it's 0 indexing, tells me all the different stuff that I can play around with, including this vast array of historical and scientific data or metadata. So again, this is simply trying to model the idea of getting a hold of a data set and then sort of from scratch understanding what's going on there. Okay. Now let's see if this works. Okay, good. So this is Argo salinity. It's one of the profiles. It's a single profile from a particular platform, platform number 1. And so I can go up to platform number 1, profile number 9, or number 14, or number 20. But as I mentioned, there's actually 9 different Argo drifters that were in the area. So some of the code up above took all 9 of those and sorted their profiles in time order. So instead of just doing platform number 1 or platform number 7, I can do all the profiles for a single platform. So that smooshes them all together. And I can also do all the profiles for all 9 platforms. And you can see that platform 1 only had 1 dive, but the second platform had 29 dives, and so on. So this is 9 different Argo drifters that are in the area, each of which has its own number of profiles over the course of a year, all smooshed into one graph. Okay. And then that's showing a graph with 2 different vertical axes. So it's showing both the salinity and the temperature. And again, I've got this little slider here so I can pick a different time. And that brings me to my final cell. And the thing that didn't work up above was basically comparing the vertical shallow profiler data to the GLODAP data, and there's a definite disparity, but I'll have to sort of reharmonize all the data so that that's available to you if you're interested in exploring that. But as I say, the grand project here is to create enough notebooks that are readable and also are creating these comparisons between these different contemporaneous and co-located resources to see, do they really compare with one another? And that's kind of where this is headed. So the last cell that I ran here creates a leaflet map. It's a bit on the large side, but it also pulls out of the Argo data, the Argo profile locations, and it ties them together in these little daisy chains. And simultaneously, there are dots corresponding to the cabled array locations, as we work on that. So this is the axial seamount, axial base, and then over in the caldera. And then this is the Oregon slope base and the hydrate ridge and the endurance offshore site. So the next step with this would be to be able to create little drawing tools and so forth to start querying the data and looking at it further, and then to go from this to MODIS and so on from there. So hopefully this has been, at least parts of this are of interest, and the main value of what I'm presenting here is intended to be a collection of notebooks, and it'll be cleaned up, that you can use as a resource for thinking about how to approach a data set, how to break it open and sort of get at the stuff inside, understand the metadata, work your way through that, and then how to start thinking about comparing one data set to another using some of these things that are built into Xarray. So for example, the nearest method, where you can say, okay, give me the nearest point from this data set to that data set, and the nearest in time and space and so forth. So anyway, that's what I was hoping to share with you. I'm right at 12:30, so we can go have lunch now. Everything good? Okay, thank you so much for your time.